Hi, folks. Welcome to 1.7 Inverse Functions, Part 1. So, as usual, we're going to start with a what we know, all right? And so a brief list of the things we've covered so far in Chapter 1. We've taken a look at relations, functions, and specifically one-to-one functions. We've looked at domain and range in a number of ways, including from an equation, using numbers, and from a graph. And we've looked at combining functions with this algebraic operators, all right? So that's just when we add, subtract, multiply, divide, so addition, subtraction, multiplication, and division. And then looking at the function compositions where we actually put one function inside of another function, okay? So if you remember, f of g of x is actually the same thing as writing f composed with g of x, okay? And lastly, we talked about parent functions and their graph transformations. And I would say out of all of this stuff, the things that are most important today, we're going to look at this algebraic, numeric, and graphical. So looking at multiple representations, we're going to be using our function compositions and some information from 1.1 to really think about what is an inverse function? Okay, so that is our main question for today. What is an inverse function? And then what are some strategies that we can use to find them in those three representations, all right? Numbers, graphs, and equations. All right, let us begin. First up, we're going to talk about notation and definition of inverse functions. So the basic gist of it is that inverse functions allow us to undo other functions, right? And what I mean by that is, let's use some examples, all right? So addition and subtraction are a pair of inverse functions. When I add something and then I subtract that same something, I get rid of the addition. Same thing if I were to multiply by, let's say, 2, and then I want to get rid of that multiply by 2, I'm going to divide, division. I'm going to divide by 2. So multiplication and division, that's another pair of inverse functions, all right? Square, so when we do like x to the power of 2 and a square root, those undo each other, all right? And if you've had trig, this might look familiar. Sine and inverse sine. So that's how we undo this function of sine, okay? So these are all some examples, but in general, the notation we use to describe functions and their inverse functions looks something like this, okay? So we're going to write it like f with a little minus 1 of x is the inverse function of regular f of x, okay? And so if we want to bring some colors in here to make sure that we are seeing the right piece of information, this minus 1 is the part that means inverse function, okay? Now, when we say inverse function, again, that's a function that undoes another function, but the inverse function is actually not the same as 1 over f of x, okay? In fact, this 1 over f of x, we call that the reciprocal And being able to distinguish in our heads the difference between a reciprocal and an inverse would be really important, right? Inverse, we're actually undoing something. Reciprocal, we are flipping a fraction, okay? Or we're finding the reciprocal of a fraction. All right. One last thing that I want to say about inverse functions and their functions is that if I take the function, okay, and I put that output into the inverse function, right, I should get whatever I put into the original function back out. And similarly, if I take the inverse function and I put it inside the original function, or I compose it with the original function, I should get the same thing I put out, put into the inverse. Okay. So this is sort of our golden rule algebraically about inverse functions. Okay, so if I compose a function with its inverse function, I should end up with whatever I put in. All right. So knowing that, let's move on to finding inverse functions numerically. All right, so how do we find them using a number? Well, it turns out that if the point, let's say A comma B is on f of x, right? So we have some point, A comma B, that's on f of x. Then it turns out that B comma A is on the inverse, the inverse function, okay? Now, one thing I really want us to see here is that if A comma B, now let's do this differently. If A comma B is on the function, then B comma A is on the inverse function, meaning I take my x and y values and I switch them, I'll get a point that is on the inverse function, okay? Now, let's take a look at a few examples, right? So if 0 comma 1 is a point on f of x, right? So we've got our 0 comma 1 is on f of x, then something else is a point on the inverse function. And that would be 1 comma 0, because I switch my x's and y's, right? Now I want to combine this with this idea right here, that if I compose the two functions together, I should get the same thing back that I put in originally. So let's see. If I take f of 0 and I put that into the inverse function, let's see what we get. So we're going to do the inside piece first, right? So we still have our inverse, but f of 0 is 1 because the point 0 comma 1 is on the graph, right? And according to this, the inverse function, when I plug in 1, what do I get back out? Well, I get 0. Okay. And let's try the other way. If I take the inverse function and I plug in 1, and then I take that output and I plug it into the original function, let's see, we get f of 0, because I'm putting 1 in there, and according to this other point, f of 0 is 1, right? So in both cases, I hope we can see that whatever it is that we put in, we get back out. Whatever it is we put in, we get back out, all right? All right, let's take a look at example 2 here. If 3 comma 9 is a point on f of x, then 9 comma 3 is a point on the inverse. All right, so 3 is the x value in the original, but it is the y value in the inverse. Oops. And 9 is the y value in the inverse, but the x value in the, or it's 9 is the y value in the original, but the x value in the inverse. All right, let's try composing them both ways again and see what we get. So inverse of f of 3, f of 3 is 9, so inverse of 9 is 3. That checks out. All right, so 3 in, 3 out, and f of the inverse of 9. All right, so this gives f of 3, which according to our other coordinate is 9. So 9 in and 9 out. All right, if you want to take a look at examples 3 and 4 on your own, this is a good time to pause. You can come back and check your answer. Otherwise, let's go ahead and do these together. All right, example 3, if negative 2, 4 is a point on f of x, then 4 comma 2 is a point on the inverse. And we get negative 2 as the x value. Oh, this should be a negative 2 over here. All right, as the y value. And then 4 as the y value, and then 4 as the x value. All right, let's compose them and see. The inverse of f of negative 2 is the inverse of 4, which is negative 2. All right, so whatever we put in is what we got out. And the other way around, f of f inverse of 4, right? F inverse of 4 is negative 2. F of negative 2 is 4. So I put in 4, I compose the functions, and I get out 4. All right, last but not least, if negative 8, negative 10 is a point on f of x, then negative 10 comma negative 8 is a point on the inverse function. X value, y value, x value, or sorry, y value, x value. All right. So we've swapped the x's and y's, but now let's go ahead and compose them and make sure we get the same thing. Inverse of f of negative 8 equals inverse of negative 10, which is inverse of negative 10 is negative 8. All right, that works. I put in negative 8, I compose them, I get negative 8 out. And now we do the other way, f of f inverse of negative 10, which is f of negative 8, which is negative 10. I put in negative 10, I leave with negative 10. All right. And this, my friends, seems like a good stopping point for part 1. Come on back for part 2.